Buenas tardes a todos. Les damos la más cordial bienvenida a esta sexta edición de la Cátedra Patrimonial Douglas Osheroff. Me permito presentar a las autoridades que nos acompañan el día de hoy. Está con nosotros la doctora Imelda Olivas Armendáriz, jefa del Departamento de Física y Matemáticas. Nos acompaña el doctor Miguel Domínguez Acosta, jefe del Departamento de Ingeniería Civil y Ambiental. Está con nosotros el doctor Erwin Adán Martínez Gómez, jefe del Departamento de Ingeniería Industrial y Manufactura. El maestro Ismael Canales Valdivieso, jefe del Departamento de Ingeniería Eléctrica y Computación. El doctor Martín Heilmaier, profesor doctorado en Ingeniería, invitado del Instituto de Tecnología de Karlsruhe. El doctor Juan Francisco Hernández Paz, director del Instituto de Ingeniería y Tecnología. Nos acompaña también el doctor Daniel Constance Cortés, secretario general de esta universidad. Y muy en especial al maestro Juan Ignacio Camargo Nazar, rector de nuestra universidad. Le solicitamos al doctor Juan Francisco Hernández Paz nos dirija unas breves palabras, por favor.
Buenas tardes, tengan todos ustedes, con el permiso del Presidium que ha sido debidamente presentado. Pues antes que nada quiero agradecerles el que nos acompañen hoy en esta sexta edición de la Cátedra Patrimonial Douglas Osheroff. Esta cátedra, pues, es una cátedra muy importante para el Instituto de Ingeniería y Tecnología. Fue la primera cátedra que se instauró en este instituto y conmemora, pues, prácticamente todas las hazañas y logros científicos que se han ido dando, pues, a través del tiempo y a través, pues sí, de los últimos 6, 7 años que se han venido haciendo en el mundo científico. Conmemora prácticamente al doctor Douglas Osheroff y su gran aportación con un material superconductivo que es usado prácticamente en todos los cohetes y en las misiones espaciales con el hidrógeno. Esta cátedra se ha distinguido por traer invitados de gran nivel de muchos países, incluye al doctor Osheroff, al doctor Croto, a la doctora Cheto, al doctor Schwartz, al doctor Barry Carter y ahora nuestro invitado del día de hoy, al doctor Martin Heilmaier, que nos viene acompañando de Alemania, y son gente que se ha distinguido mucho por su quehacer y por su labor científica en su área de expertise. Les agradezco mucho. I want to thank you very much to Professor Heilmaier for being here today. Thank you very much, Martin. I know that the trip was long and tiring, that you had a delay at Dallas, but fortunately you are here with us today. Thank you very much. Willkommen in Mexico. I know that I know a little bit, very little German. Thank you very much for being here. Y quiero decirles, pues hay que aprovechar a nuestros invitados. El profesor Heilmaier, aparte de ser un gran científico, un gran experto en metalurgia, es una persona muy interesada en establecer vínculos con México y con su comunidad científica y con sus estudiantes. Entonces, eso es parte fundamental de la Cátedra Osheroff. No solo traer científicos de gran nivel, sino potencializar las capacidades de intercambio y las capacidades de colaboración con instituciones fuera del país para hacer más grande nuestra UACJ. Les agradezco mucho el que estén con nosotros y siguiendo el lema, todos somos UACJ, y espero aprovechen mucho esta ocasión la cátedra. Gracias.
Enseguida le solicitamos al maestro Juan Ignacio Camargo Nazar nos dirija un mensaje y de la inauguración de esta cátedra.
Muy buenas tardes a todos y a todas. Me da mucho gusto saludarlos. Saludo con gusto a la doctora Imelda Olivas Armendáriz, jefa del Departamento de Física y Matemáticas. De igual forma al doctor Miguel Domínguez Acosta, jefe del Departamento de Ingeniería Civil y Ambiental. Al doctor Erwin Adán Martínez Gómez, jefe del Departamento de Ingeniería Industrial y Manufactura. Al maestro Ismael Canales Valdivieso, jefe del Departamento de Ingeniería Física y Computación, al señor director del Instituto, el doctor Juan Francisco Hernández Paz, y también agradecer la presencia del doctor Daniel Constance Cortés, secretario general de esta universidad, y en especial al doctor Martín Heilmaier, que nos visita del Instituto de Tecnología de Karlsruhe, Alemania. Gracias por estar aquí en esta su casa, la Universidad Autónoma de Ciudad Juárez, y bienvenido también, doctor Martín Heilmaier, a Ciudad Juárez. Gracias por estar aquí. De igual manera, saludo con afecto a los funcionarios, a los maestros, maestras que hoy nos acompañan. En especial quiero agradecer al doctor Manuel Antonio Ramos Murillo su colaboración para la realización de esta cátedra. También agradecer la presencia del doctor Rurik Farías, secretario general del sindicato, y desde luego a mi aprecio y mi reconocimiento a las y los estudiantes del Instituto de Ingeniería y Tecnología que nos acompañan en esta ya tradicional cátedra en la universidad, no solo en el instituto, la Cátedra Patrimonial Douglas Osheroff. A todas y todos bienvenidos a este importante y trascendental evento. Decirles que para la Universidad Autónoma de Ciudad Juárez, en particular para el Instituto de Ingeniería y Tecnología, el poner en marcha esta cátedra Douglas Osheroff ha significado no solo un acto de reconocimiento a la trayectoria de un personaje en la ciencia, sino también la posibilidad de sembrar en nuestros estudiantes, en nuestros maestros y maestras, el interés por el conocimiento, y en esta cátedra en especial divulgar el conocimiento científico de frontera en el norte de México a través de la impartición de conferencias magistrales de visitantes muy distinguidos a nivel mundial. Y bueno, las cátedras patrimoniales dentro de la Universidad Autónoma de Ciudad Juárez se han convertido al paso del tiempo en espacios de discusión, de intercambio de ideas y conocimientos que indiscutiblemente han repercutido en el nivel académico de los profesores y profesoras, de los alumnos y alumnas, pero no solo esto, sino que ha despertado también un interés en la teoría y en la práctica de cada una de las disciplinas. El instaurar una cátedra patrimonial es un proceso que se sigue en el Consejo Académico de la Universidad, en donde se plantea por parte de alguno de los institutos la necesidad del establecimiento de esta cátedra y sobre todo el reconocimiento, la trayectoria del titular de esta cátedra patrimonial. En el caso de la cátedra patrimonial del profesor Douglas Osheroff, es ya una cátedra que es emblemática para la universidad y para el Instituto de Ingeniería y Tecnología. Como lo han mencionado, bueno, el profesor Douglas Osheroff obtuvo el premio Nobel en Física en el año de 1996. Él nos acompañó en el año del 2013 y bueno, estábamos recordando ahorita en una reunión previa que tuvimos el interés que despertó esta plática, no solo con estudiantes de la propia universidad, sino también de otros institutos e instituciones de educación superior y de media superior en la ciudad. En el 2014 se contó con la presencia del profesor Harold Kroto, premio Nobel en Química en el año de 1996. En el 2015 tuvimos la visita del profesor Barry Carter de la Universidad de Connecticut. En el 2016 contamos con la presencia de la doctora Ana María Seto Kramis, que participó en 2 premios Nobel de la Paz. En el 2017 el doctor Justin Schwartz, decano de la Universidad Estatal de Pensilvania, y hoy en la 6ª edición contamos con la presencia del doctor Martín Heilmaier, del Instituto de Tecnología. Carlos, yo lo digo de una forma y luego lo dicen de otra forma, ¿no? Como lo dicen, yo tenía otros datos. Este instituto, que se le denomina el KIT, se creó en el año del 2009, que combina las tareas de una universidad del estado de Baden-Württemberg con la de un centro de investigación de la asociación Helmholtz en las áreas de investigación, enseñanza e innovación. En esta ocasión el conferencista nos dará la conferencia inaugural, que se denomina Más allá de las aleaciones de base de níquel. Tenemos opciones para nuevos materiales metálicos, para aplicaciones estructurales de temperatura ultra alta. Bueno, ustedes, yo soy médico, yo soy abogado, entonces todo esto me resulta por demás complicado, ¿no? Pero bueno, ustedes están en esto. Me da mucho gusto que nos esté visitando el doctor Martín Heilmaier. La universidad no tiene más que palabras de agradecimiento con él, que estoy seguro que no escatimará ningún recurso ni ningún momento para entregar de manera generosa sus conocimientos a nuestros estudiantes. Y bueno, también quiero mencionar, tuvimos ahorita una plática con él, también la disponibilidad de su instituto de recibir estudiantes de pregrado, de posgrado y profesores para realizar estancias de investigación que promuevan el enriquecimiento científico y académico y cultural de México y Alemania, particularmente entre el KIT y la universidad. Y bueno, sirve también para posicionar a nuestra universidad y a quienes integran la comunidad universitaria como una promotora del conocimiento más allá de los libros, de la interacción que se da en las aulas entre académicos y alumnos, la posibilidad de difundir estos desarrollos tecnológicos. Y bueno, como ustedes saben, la universidad a su corta edad, a 46 años de su fundación, está avanzando a un paso muy firme en su misión de mantenerse entre las mejores universidades del país, y eventos como este nos prestigian, y por lo que, bueno, este tipo de cátedras patrimoniales seguirá el apoyo a esta cátedra del doctor Douglas Osheroff, y también el impulso a otras cátedras patrimoniales en las distintas áreas del conocimiento que tiene este instituto y los otros institutos de la universidad. Bienvenidos a todas y a todos por estar aquí. Les deseo éxito en esta cátedra, y bueno, vuelvo a reiterarle mi agradecimiento al profesor Martín Heilmaier por su generosidad, por estar aquí, por el esfuerzo que hace para venir a Ciudad Juárez y poder continuar con el desarrollo de esta cátedra patrimonial. Muchas gracias a todos y a todas. Espero que sea de mucha utilidad, y sobre todo a los alumnos y alumnas que aprovechen estas oportunidades que brinda la institución, el poder tener personas de gran renombre, con mucho conocimiento, y que puedan sembrar en ustedes esta semilla de la investigación que esperamos que pueda germinar a un corto plazo. Muchas gracias a todos y a todas. Gracias. Y bueno, para cumplir con el acto inaugural, les pediría si podemos ponernos de pie. Gracias. Siendo hoy lunes 11 de noviembre del 2019 a las 12:45, declaro formalmente inaugurada la Cátedra Patrimonial Douglas Osheroff en su edición 2019. Muchas gracias a todos y a todas. Cuando termine. Bien. Una última solicitud. Me piden que haga entrega de esta placa de agradecimiento al doctor Martín Heilmaier. Dice la Universidad Autónoma de Ciudad Juárez, a través del Instituto de Ingeniería y Tecnología, otorga la Cátedra Douglas Osheroff 2019 al profesor Martín Heilmaier del KIT por su destacada conferencia, más allá de las… No puedo meter… Este es el nombre de la… Es el mismo, ok. Ok, dice, do we have option for novel metallic materials of ultra high temperatures structure application, Ciudad Juárez, Chihuahua, 11 de noviembre del 2019, por una vida científica, por una ciencia vital.
Agradecemos a los funcionarios de nuestra universidad su presencia en este evento y continuamos con la conferencia del doctor Heilmaier.
Welcome everybody. I hope you can hear me in the back. I hope also that the slides are large enough for you to view it from the back. Otherwise, I would recommend you to come a little bit up front. But anyway, before I really go into the scientific content of my talk, which has already been mentioned, beyond nickel-based superalloys, do we have options for novel metallic materials for ultra-high temperature applications? I would like to thank you very much to all of you for coming here, for listening to my talk, and of course I would like to thank the Presidio, the Rector, and all the other people who have been awarded me this prestigious nomination for the Douglas Osheroff lectureship. I'm hoping to satisfy the demands connected with it. And before I go into, as I said, scientific details, let me just briefly introduce where I'm coming from, where I'm currently lecturing. And this is all Karlsruhe in different views. This is the famous Karlsruhe Castle as a live image. This is the plot from the top where you can see how the city was designed. The city was designed around the castle. So this is the castle from the top, and the city is looking like a sun which has its branches separated or distributed amongst the city in a circular way. So the city is kind of organized as a circle with the center as the castle, being the castle. And this is just a view of how our university looked like in the 19th century. Actually, the foundation was laid in 1885 as a technical Hochschule, technische Hochschule, technical high school, so to say. So it wasn't a, and this is written down here, so it wasn't a university until the 20th century. This is important to realize. Okay, now, where is Karlsruhe related? So here you see a kind of a sketch of Germany with the border to France. So here is the Saarland, Saarbrücken, as Francisco would know. Yeah. Here is Karlsruhe, so pretty close. KIT means Karlsruhe Institute of Technology. Yeah. This is the abbreviation of it. And I have plotted for comparison Frankfurt, because many of you who will travel or who may travel to Germany will land in Frankfurt, which is somehow, well, close to the center of Germany, and from there it's an easy ride down to KIT by direct trains, high-speed trains, ICE trains, as you know, which reach out to Karlsruhe from Frankfurt Airport within less than 1 hour. Here's the border to Switzerland, here's Poland, here's Austria, and so on and so forth. You probably are familiar with Germany a little bit. Okay. Karlsruhe as a city has a population of about 250,000 or maybe 300,000 at most, depending on how you count it. So it's certainly much smaller than Ciudad Juárez here. Okay? Good. Now, Karlsruhe, KIT, Karlsruhe Institute of Technology, we did not carry this name until about 15 years ago, because we were formerly separated institutions, a university on one side, which is located downtown city. This is Karlsruhe. And actually the castle is just on the edge here, on the edge of the campus. So if you once have the chance to come to Karlsruhe and have a chance to stay overnight in the Gastdozentenhaus, in the guest house for the scientific staff, you can have an easy walk to the castle, basically being only 200 meters away. It's very green and very refreshing, very quiet place. But of course, on the other hand, you have the downtown area close by, also within walking distance. And apart from that, we have a second institution which was independent to the university, and this is called the so-called Helmholtz Center. This was also briefly addressed. And the Helmholtz Center, as you can see, is not far away, only 12 kilometers, but it's located in the woods. This has a simple reason. About 30 years ago, Germany was still very much into nuclear power research, nuclear fission and nuclear fusion research. This was top secret at that time, and that means it had a research institute like this devoted to nuclear fission research and fusion research had to be placed in some remote place where not much population is around. Meanwhile, this has changed, so you can just enter this site as well, like Manuel did many times with showing his passport, and then you get easy access. No complications with certain specific regulations and so forth. Now we have merged to form KIT, and that's why we call it 2 missions and 3 challenges today. So we are doing research. The Helmholtz Center is mostly devoted to research. We do education. This is mostly part of the university. And we both together do innovation. Innovation means patenting, developing new products for applications into the real market. Yeah? And I'm working in all the 3 of these aspects, which I will show you in a minute. Last slide on KIT, some facts and figures. We have about 10,000 employees, including third-party funded people, right? Like PhD candidates, postdocs, and so on and so forth. We have 360 professors. We want to increase that number by about 100 in the next 5 to 7 years. So we are aiming to expand. We have about 25,000 students, more than 10,000 of them are in engineering disciplines. Amongst them, again, the mechanical engineers are the most frequent ones, about 6,000 in total. And we have, of course, a lot of natural science students, physics, chemistry, biology, and so on. Our total budget a couple of years ago was 861 million. This is very important, the one here. The funding is actually distributed into 3 big parts, right? The first part is from the federal government, which funds the Helmholtz Center. So 30% of 860 million, you can calculate this number, is only for research in a research institute. Another 30% is for the university. This comes from the local state. In Germany, like in Mexico, all universities are funded from the local states, not from the federal government. And both team up and add on this by raising third-party funding from various sources, industry as well as national science foundations, and these assume about 40%, right? Quite a bit fraction of the total budget comes from third-party funding. That's why we are, I think, strong in fundamental as well as in applied research. And now coming to my talk itself. What is the motivation of my talk? This can be best described by this little sketch here, where you can see the specific core power of a turbine engine. I'm working in high temperature structural materials, as the title suggests already. So this is the specific core power over the turbine inlet temperature. And what you can see here is these dots here are all coming from certain metallic materials used at a certain time of development, like in the 50s, 60s, 70s, and so on and so forth. What you can see here is that there is a demand of increasing the turbine inlet temperature by developing more and more advanced materials. But what you can also see here is that you never reach the ideal performance, which some of you may know from textbook knowledge on thermodynamics. This is the thermodynamic curve for a combustion engine, so to say. So in fact, we observe that we don't get even closer to that gap. The gap opens actually, and this is simply due to the fact that you have inefficiency losses. Heat is wasted somewhere, and so on and so forth. No engine, as you know, we do not have perpetuum mobiles. No engine works at 100% efficiency. The question is, how high is the efficiency, and how can we increase the efficiency? And the development trend suggests that these inefficiency losses become more and more while increasing the temperature. And this is simply due to one fact, namely that the alloys which we currently use, the nickel-based alloys, are limited by their Solvus temperature of the strengthening phase gamma prime, meaning we reach the maximum operation temperature of these alloys. We need to develop new materials, alternatives to nickel-based superalloys, which have a much higher melting point, and thus provide high creep resistance, oxidation resistance, and other properties. Reasonably low density, because you don't want a really heavy engine, because this will never fly, right? So the engine has to be light. And yesterday I arrived in Dallas using the Boeing 787, also called the Dreamliner. And in this Boeing 787 there's a really novel and the most innovative material in the aero engine, which is called titanium aluminides, a low weight material with a density of less than 4 grams per cubic centimeter, with a specific strength which exceeds that of nickel-based superalloys by a factor of 2 at best. Obviously, I arrived here safely, so this worked, right? And we now try to develop new options for these metallic materials with higher melting points than superalloys. And I have splitted my presentation into 2 parts. First part will be placed on refractory metal silicide alloys. Second part on what we call high entropy alloys, a really novel research branch which hasn't been discovered until 10 years ago. Before I go into this, I will show you one slide on why nickel-based single crystal alloys are so good. And this is the answer to it. This is the micrograph, a TEM, transmission electron micrograph of a nickel-based single crystalline alloy which is called CMSX4. CMSX4 stands for Canon Muskegon Corporation Single Crystal number 4. Number 4 because they developed a series of alloy compositions, and some of them were successful, some of them were not successful. Obviously, the number 4 alloy with this chemical composition was extremely successful because it now represents the state-of-the-art material in the hottest section of an aero engine. Those of you who fly, no matter what kind of airline, no matter what kind of aero engine, made by different manufacturers like General Electric, Rolls-Royce, Pratt & Whitney, to mention a few, will use significantly other materials than this nowadays in the hottest section. But they are limited to keep the strength up by this phase, which is called the gamma prime phase. It's an ordered intermetallic phase embedded into a matrix of a disordered solid solution. Disordered solid solution means, for those who are not material scientists, the atoms which are in the alloy are randomly placed on the lattice sides. Yeah? There are no specific locations for specific atoms, which is different for the gamma prime phase. Here you have 2 different atomic sites which are occupied by 2 different atoms. There's one side which is mainly occupied by nickel and chromium, and the other side is mainly occupied by aluminum and titanium. I don't want to stress your knowledge on materials too much. I leave it like it is now. But by just saying one more thing to all these other chemical elements which have a definite task to fulfill. For example, those elements, molybdenum, rhenium, tungsten, are heavy elements, are big atoms, and they strengthen the matrix, this little fine white area here, by solid solution strengthening. I will come back to that in part 2 of my lecture again for the high entropy alloys. So, keeping in mind, the take-home message here is, if this strengthening phase, the gamma prime phase, is gone, if it is dissolved at temperatures beyond, say, roughly speaking, 1200 degrees C, this material is no longer strong. It's weak. Therefore, it cannot be used. If you want to go to higher temperatures to increase the efficiency, you cannot make use of this alloy anymore. You need new alloys. That's the way how, or the reason why I'm looking into alternatives to it. So I'm coming to the first part. I apologize for the small letters here. You probably cannot read it in the back, but I just draw your attention on the most important issues. So what are the most important issues? First of all, these alloys have a high melting point. Molybdenum has a melting point as a pure element of over 2,600 degrees Celsius. Having just said that nickel-based alloys have a temperature limit of 1,200 degrees Celsius, roughly speaking, this is much higher. Now, a pure molybdenum-based material would not work in a high-temperature environment because of the following issue. You need suitable oxidation resistance. If you don't have material elements, chemical elements in the alloy which provide oxidation resistance, the alloy would oxidize rapidly. You would form, in particular in this case, a volatile molybdenum trioxide which just sublimates and goes away. So you form smoke of molybdenum oxide which rapidly evaporates. You need silicon to avoid this, but you need a high amount of silicon, above 35 atomic % silicon, to get a silica scale formation here, which is a lot. Yeah? So we try to avoid this because this material becomes extremely brittle. What else could you do? You could add other elements to alleviate this factor to alleviate the fact that you need high silicon contents. For example, you could add boron. Boron is used for accelerating the coverage of the non-oxidation resistant microstructural constituents. Boron lowers the viscosity of the oxide scale which forms and thus provides rapid oxidation protection. But now there is a drawback here, again a small number. Rho, this is the density, the specific density of the alloy, mass divided by volume, is 9.5 grams per cubic centimeter. This is beyond the density of nickel-based alloys. Roughly speaking, nickel-based alloys have a density of 8 grams per cubic centimeters. So you need to do something to make the alloy lighter, not that heavy. And this can be done by titanium, for example. Titanium addition changes also the phase formation somehow, but you can avoid this by playing around with the phase diagram. I don't show this slide here. But then at the end, the density is down to 7.4, which is lower than nickel-based superalloys. So we have an alloy which has a potentially higher oxidation, higher creep resistance, mechanical strength at high temperature, but has a lower density already. Now you could ask yourself, why at all do you need the boron? And this is what I will show you in the next few slides on this first part. Namely, you can still achieve good properties with a simple ternary alloy consisting of molybdenum, silicon, and boron. The titanium, if you don't use the boron, stabilize a different phase than this one here. This one is an oxidation-resistant phase, and the question was, an unsolved question in science, whether this titanium 5 silicide is good or not in the alloy. If you synthesize a pure titanium 5 silicon 3 phase, this would oxidize rapidly at temperatures beyond 1000 degrees. I will show you that this is surprisingly not the case for the alloy of interest here. Okay, I have to bother you with one phase diagram at least. Maybe you see a second one. So this is a melt projection of the ternary phase diagram between molybdenum, this is on this scale, silicon shown on this scale, and titanium shown on this scale. And when you look at the melt surface from the top, say from very high temperatures, you see different lines here, and these different lines reflect reaction pathways in the alloy. And we picked out two of the interesting ones. Those here are not so much interesting because we don't want to go into very high silicon contents, and we don't want to go into low titanium and molybdenum contents, so we are interested in this part here. The green part, which gives you an eutectic reaction. Everybody should know what a eutectic reaction is. A liquid, when you cool down a liquid, it phase separates into two solid phases. In this case, it's molybdenum solid solution, disordered, and an intermetallic compound of Ti5Si3, the one I mentioned on the previous slide. And on the other side, you see the blue range, the blue area here. This is an eutectoid reaction taking place. So the liquid first forms a monolithic intermetallic compound of chemical composition, nominal chemical composition MO3Si, and this later on phase separates into two other phases at lower temperatures, namely the MO5Si3 intermetallic compound. This looks pretty much similar to the Ti5Si3. However, the molybdenum is replaced by the titanium, and again a molybdenum solid solution. And these are the microstructures which form there. The striking feature in this slide, without going too much in detail, is, and this is why it's plotted on a relatively small scale, this is an ultra-fine microstructure in both cases. Here in an as-cast situation and here in a heat-treated situation. And you see already, according to the heat treatment temperature, 1300 degrees Celsius for 200 hours, you need a very high temperature for long times to get the thermodynamically stable two-phase microstructures consisting of those two phases for this alloy. This points already to the fact that we have a much more stable microstructure in these molybdenum-based alloys than in the previously shown nickel-based superalloys. At 1300 degrees Celsius, the nickel-based superalloys is nearly about to melt, right? So here you need this for this long time to form the thermodynamically stable microstructure. Okay. And you can do it by casting. So this is all cast alloys, nothing special, no powder metallurgy, nothing. Okay. So here in a larger magnification, the fine-scaled eutectic microstructure. This is the alloy composition. Those of you who have looked clearly or carefully would see all of a sudden, this is in atomic percent, all the concentrations I give are in atomic percent. If you would now calculate the molybdenum content, you would say, this is only about 30% molybdenum. Is this still considered a molybdenum alloy, or is it rather already a titanium alloy? In terms of atomics, or atomic numbers, it's a titanium alloy. In terms of weight, if I would calculate weight percent, it would be still a molybdenum alloy. And since we are doing casting, you know, all the metallurgical engineers talking in weight percent and not in atomic percent. So we can still say this is a molybdenum-based alloy. Okay, so we, of course, did some calculations. I don't want to stress you too much with details here, but the eutectic transformation depends, of course, strongly on the chemical composition. For this particular alloy, the melting point is on the order of 1900 degrees Celsius, so pretty high compared to the nickel-based superalloy. And we get a very fine-scaled microstructure with these lamellae here. This is the scale bar here, 40 microns. This is still a scanning electron micrograph. And of course, the dark phase we determined by EDX and other methods is titanium 5Si3 together with some molybdenum, which assumes titanium sites in the crystal structure. And the light phase is molybdenum, mostly molybdenum plus some titanium and silicon. Okay, so for the moment, keep that in mind. We have a very fine-scaled microstructure, and the question is, how does this microstructure, this fine-scaled microstructure, perform at elevated temperatures with respect to creep and with respect to oxidation resistance? Compared to that, the eutectoid alloy, you can see, has a much higher molybdenum content. Here, silicon plus titanium together is about 55, so that means 45 atomic percent is still molybdenum. And I said previously, at the beginning, this is the as-cast microstructure. The as-cast microstructure did not fully decompose into the thermodynamically stable phases. That's why we needed this 1300 degrees Celsius heat treatment. Here you see this light phase, the light gray phase. This is still molybdenum 3 silicon, and you need to decompose this into the stable phases, the molybdenum solid solution and the molybdenum 5Si3 phase, which has been done here. Of course, you note that there is some residual phase left, Ti5Si3 here, the very dark phase, but this is only to a minor content, 5.2. Maybe we should not do the update here at the moment. Yeah, I wait. Yeah, don't worry. Okay. So what you also can see here is that we have a mixture of about 50 to 50 volume% solid solution and silicide. So this material is a kind of a microcomposite, if you wish. Okay? Now, first I talk about oxidation, then I talk about creep. Oxidation is a major issue for these alloys because assume you have a metallic material, you put it in a furnace, and then you let it oxidize. The furnace operates like an aero engine without the revolutional centrifugal forces. So the metal is transformed into oxide. If all the metal is eaten up by forming oxides, you have a brittle material and your engine fails. So this should not occur. What this means is when I put this alloy in a furnace and I have shown you two different temperatures, 800, green is always 800, the green scale is the eutectic alloy, the blue scale, the blue color is the eutectoid alloy. I have shown two different temperatures, 800 degrees Celsius and 1200 degrees Celsius. And what you see here, the alloy, the green alloy, the eutectic alloy, does not change its weight. Here is plotted the weight per surface area, delta M over A in milligrams per square centimeters. If the weight does not change, this is an indication for a very slow oxide formation at these temperatures, right? However, compared to that, and here you see three curves plotted. Well, the third curve you cannot see because it's the eutectoid curve at 1200. It's actually underneath the other two, the eutectic alloy at 800 and 1200 degrees C. Basically what you see here, after 100 hours, not much has changed for the two temperatures of interest, and also for intermediate temperatures. But what you see is for the eutectoid alloy, this one here, this squared, half-filled square symbols, this goes down rapidly, ending up down here with a dramatic weight loss. And this dramatic weight loss is exactly what I meant with molybdenum oxide sublimation or volatile molybdenum trioxide species. This is how the material looks like at 800 C after 10 hours already. You see that the oxide scale does not adhere, it spalls off. The oxidation goes on rapidly. You form this yellow shiny oxide here on the scale. In other words, we call this alloy not oxidation resistant. It causes catastrophic oxidation at 800 C, so you would never use this alloy at elevated temperatures. But this alloy shows very good oxidation resistance. And of course, without going too much into detail, you can analyze the oxide scales here by doing advanced microstructural characterization. You don't see the oxide scale here on the top because you cannot see a silica scale. This is not easily viewable from with SEM. But what you can see is that the oxide scale in the eutectic alloy consists of silica and titania. And both oxides form a mixed scale, and this mixed scale shows surprisingly high oxidation resistance for this particular alloy. And further to that, since the oxide scale is still very tiny, so this is 20 microns, so the oxide scale is about 5 micron thick, we can conclude that molybdenum oxide evaporation is suppressed successfully. And this is something special because those who may have worked with refractory metals know that all refractory metals, niobium, tantalum, molybdenum, tungsten, suffer from this effect. They form rapid oxides, and either they spall off the surface or they do sublimation and disappear. So this is not shown here, and this was found out for the first time for this particular alloy. Of course, you can also look at the 800 degrees Celsius oxide scale. It shows, again, protectiveness by forming these duplex scale layers. I don't want to go too much into detail. If you have any questions, I would be happy to answer them afterwards. Let me show you instead the creep behavior for these two alloys. And now, as always, a metal has two sides, right? On one side, it's shiny. On the other side, it's not so nice. The drawback of this eutectic alloy comes with the creep behavior. What is plotted here? Here you see a creep curve for a constant stress of 150 megapascal. This is approximately the stress a turbine blade in an aero engine would see at start of and landing events when you need the full power of the engine. Of course, when you cruise at high altitude, you need much lower stresses because then you don't run at full revolutions yet. Okay, at 1200 degrees Celsius. And then you see that we plotted here the creep rate, meaning the rate of extension, plastic deformation of the sample with respect to time or strain. Here I plotted the strain. What then you will see is that the creep rate of this eutectic alloy is much greater than the creep rate of the eutectoid alloy, which is not good news. You would like to have creep rates very much down here, meaning it would take a long time to see a creep strain of, say, 5%. Imagine a turbine blade in a rotating environment. This turbine blade starts elongating while you apply the rotational, the centrifugal load, right? So it cannot elongate infinitely because there's a casing which the blade will scratch on, right? When the casing, when the turbine blade reaches the scratch, it either breaks into parts or it scratches the casing. In any case, it needs to be replaced. So we need small plastic strains and low strain rates. So everything which is very much down low here is good. And the bad news here is that the eutectoid alloy, the one which is not oxidation resistant, is good. The eutectic alloy is not so good. Okay? This you can plot in a different way here. I've shown you all the simple, all the experiments which we made. So each data point reflects one creep test at elevated temperature, 1200 C. And here we plotted the minimum strain rate, this point here or this point there. So this is the slowest creep rate we can have. It's a predominant data point here in this creep curve. And we plotted this on a log-log scale. So strain rate plotted versus stress means we want to have the material being down here on the left, actually down here on the right lower end. Right? So you can see that the blue curve, the eutectic alloy, performs much better than the green curve, the eutectic alloy. And you can understand why this is the case. Because in the green alloy, somehow the Ti5Si3 intermetallic phase is the major phase, and the green alloy obviously performs similar to the monolithic intermetallic compound Ti5Si3. Whereas in the blue alloy, the molybdenum solid solution or the MO5Si3 are the constituents of this alloy, and as you can see here, the blue alloy shows exactly the same creep behavior than the molybdenum and the MO5Si3. So you can understand why one alloy is better or superior than the other. And that's the main issue of this slide here. Okay, then of course it all comes down to density. So I plotted here the specific strength. Sigma, the stress level, the centrifugal load, over density versus strain rate. And what you see here is that indeed our alloys are already as good as the CMSX4 at 1200 C or even better. So here are data points for the nickel-based single crystal alloy, and our material, the eutectoid, and other material with some additional amount of boron are much better. So we do have potential for being superior to nickel-based superalloys, for being able to replace them in high-temperature environments. Now you can stretch this a little further. I will keep that story short because I want to continue with my second part. You can, of course, walk along this decomposition line. Here you have got the eutectic alloy. Here is the eutectoid alloy. And I told you the eutectoid alloy would be stronger but not creep resistant. So it would be stronger but not oxidation resistant. This is weaker but oxidation resistant. So maybe we can make a compromise and locate ourselves with alloy A and B in red and black somewhere in the middle between this eutectic decomposition and the eutectoid decomposition. And of course then the microstructure looks like this, that it is composed of eutectoid regions and eutectic regions. I don't want to stretch these details here. Now let's look at the oxidation data again, because this is the initial proof. We want a non-pesting oxidation-resistant alloy. And to our surprise, we can afford with some eutectic regions still. This alloy here, the alloy A, does not show pesting at 800 C. It still shows no weight change here, but the alloy with too much eutectoid areas in the microstructure does show pesting again. So, and this the same behavior as previously was shown for 1200 C. We do not see any weight change, any noticeable weight changes. These are all small numbers here. So the material is quite oxidation resistant at the highest temperatures. But you can imagine a turbine has to be ramped up and cooled down. So you have to go through the 800 degrees centigrade region sooner or later with your alloy. So it doesn't help you having an alloy being oxidation resistant at 1200 C. At 800 it must show at least some oxidation resistance, because during start and landing you will see, the alloy will see this temperature. Okay, I skipped that for sake of simplicity. We could calculate, we have done a simulation how oxidation protection works in detail with the titania and the silica, and I do not want to go into detail, but believe me, this is just under revision in Acta Materialia, which we published recently, and it's under revision now. We provided a model for explaining why this material, the one is oxidation resistant and the other is not. I just want to skip these slides due to the sake of time, and would like to address another point before I come to the second part of my lecture, namely, how can we explain the different creep behaviors in a more quantitative way for the eutectoid alloy and the eutectic alloy, and for the new alloy A. So first of all, the new alloy A, as you can see, which is oxidation resistant still, but contains eutectoid regions, shows a better creep performance than the eutectic alloy. The reason why this is the case is very simple, because the melting points of all these alloys are different. The melting point of the eutectic alloy is lower than the melting point of the eutectoid alloy. And the melting point, when I say melting point, I mean the point where the first phase starts to melt. You know, of course, this is a melting range where the alloys start to melt. The melting point, in my definition, is the the temperature where the first phase starts to melt. So we operate these alloys at different, what we call homologous temperatures. Homologous temperature is a temperature normalized temperature, the actual temperature divided by the melting point. And of course, the comparison is only fair when you compare the alloys at homologous temperatures which are equal. So this alloy, for example, the red alloy with this temperature has a homologous temperature of 68%, 68% of the melting point. Now, the green alloy, the eutectic one, has a homologous temperature of 74% of the melting point. We made a simple test. We increased the temperature for this alloy to the same homologous temperature for the eutectic alloy, and this is shown here. This was then the creep response. Actually, the red alloy falls exactly on the line of the green eutectic alloy, meaning by definition the creep resistance is not different if you compare it in a physical straightforward way, in a physical related way, meaning at same normalized temperatures. The creep resistance, of course, is better when you let an alloy creep deform at a low absolute temperature with a high melting point. Okay, so summary of part one. We did arc melting, so this is a simple process. We have polycrystals, no single crystals, like in the case of nickel-based superalloy. Nobody knows what happens when we try to melt single crystals, but polycrystals are simply arc melted. With or without boron, they provide creep resistance superior to nickel-based single crystalline alloys at temperatures beyond 1100 degrees Celsius. The eutectic alloys offer very good oxidation resistance. They avoid catastrophic oxidation in the pesting regime. The creep behavior of the eutectoid alloy benefits from the superior performance of MO5Si3 phase as compared to Ti5Si3. And both creep and oxidation resistance can be deliberately adjusted depending on the alloy composition if I walk along the transformation line between eutectic decomposition and eutectoid decomposition. There seems to be a threshold, I didn't show this in detail, of 43 atomic percent nominally or 35 atomic percent in the solid solution for achieving pest resistance. You need a minimum titanium content to avoid pesting. That's what it says. And finally, you can describe the creep behavior by a unique and simple approach which relates the actual temperature to the melting point, the actual creep testing temperature to the melting point of the alloys. And this is called the so-called homologous temperature approach. Part 2, high entropy alloys. The concept, which is just a concept, this is not a theory, is very simple. The concept is that we get an increasing entropy configuration of the free enthalpy, delta G, for stabilizing disordered solid solution with simple crystal structures if we increase this mixing entropy. So this is thermodynamic basic principle. Free enthalpy G is enthalpy H minus temperature times and entropy S. Yeah? And the mixing entropy can be influenced strongly by what we call the so-called configurational entropy. Configurational entropy means by taking different atoms in different concentrations and put them on randomly on lattice sites in the crystal. And this is the simple formula. I don't need to explain it. So the configurational entropy actually scales with the Boltzmann constant and with the number of alloying elements, right? So just a simple comparison, a classical aluminum alloy 6082, as some of you may know, has a configurational entropy of 1.7 joule per Kelvin in mole. And what we call the classical Cantor alloy, this is a 5-component alloy in equal compositions, chromium, cobalt, chromium, iron, manganese, nickel, has a configuration entropy of 13 joule per Kelvin in mole instead of 1.7, so a factor of 10 higher. Now let's see how this concept works. So what we do at KIT is a number of different alloys. We have fundamental systems of this side. On this side, this is a face-centered cubic solid solution. This alloy is a body-centered cubic solid solution. This is a noble metal alloy, face-centered cubic solid solution. And this is some high-temperature alloys. You see all of a sudden here, again, the refractory metals show up again. Tungsten, molybdenum, tantalum, and so on. So I will look into this. I don't talk about this. How much time do I have left? 15 minutes? Is that okay? Yeah? I can speed up a little bit if you want. So the uniqueness of this approach is that we are not in the corners of a phase diagram. We are rather in the center of a phase diagram. If you go into a corner of a phase diagram, then you have the classical alloys. Classical alloys meaning steel, for example. Steel, the major alloying element is iron. And then you add a little bit of carbon, a little bit of manganese, and so on and so forth. Here the approach is, and then you are in the corner of a phase diagram, of a ternary phase diagram. This is a quasi-ternary phase diagram. Here, we go deliberately into the middle and try to stabilize a solid solution, a single-phase solid solution. And of course, we are aiming for high creep resistance, lightweight, and high oxidation resistance again. And that's why high oxidation resistance, we go for the passivating elements, aluminum and chromium. In this case, we want to form an alumina or chromia scale, which is oxidation protective. And these alloys are for high temperature creep strength. So how do we do it? Again, arc melting, quite simple. Then homogenization treatment, and then we have to check the chemical homogeneity on various length scales. For example, overall chemical composition by ICP-OES indicates that the chemical composition is quite good met here for this quinary alloy system. But we also do chemical composition on an atomic length scale, and this is what also Manuel did with us, not in this case, but in another case. This is atom probe tomography, right? So here you see the scale, 20 nanometers, and when you do the chemical analysis, you see that the elemental concentration is quite constant. It's a little bit farther away from each other than here, but again, it scatters around 20 atomic percent. And by doing so, we get a single-phase microstructure. by suppressing the competing phases which are shown here. Okay. What about the extended solid solution strengthening? Where does it come from? It comes from the fact that we mix on a random scale different atoms with different atomic sizes, right? And thereby we distort the lattice quite a bit. So lattice distortion is what counts in this system, in these concentrated systems, either BCC or FCC. And of course you have to measure the lattice distortion appropriately for predicting the solid solution strengthening. That's why we followed an experimental approach. We started from this model system, a 5-component system, and then we varied deliberately either the niobium content, so we took out niobium, and ended up at the quaternary, molybdenum, chromium, titanium, aluminum alloy, and here on the other side we took out the chromium because we wanted to suppress this phase here. The chromium to niobium phase is a Lavis phase which is brittle and which deteriorates the chemical composition. Okay, so and then just to give you a flavor of what we did, I don't want to go through the whole analysis. The atomic size difference is the measure for the lattice distortion. So a high lattice distortion means I have atoms of largely different sizes in my solid solution. So the lattice distortion is proportional to the atomic size differences, and this can be simply calculated by this formula. Here is the average radius of the alloying element, and here is the mean radius for all the alloying elements in the alloy. And this is simply summed up and then taken the square root of it. And what you see here, of course, no lattice distortion in the pure elements, so this is 0, the lattice distortion. But then, of course, the lattice distortion goes up quite a bit, up to 5%. 5% is a huge lattice distortion for a solid solution strengthened alloy. Imagine, for example, brass, copper, zinc, much lower, or aluminum, copper, much lower. Okay, and of course, with this, we can describe the increase of hardness and the hardness taken at room temperature in this case. And here you see the hardness of the pure elements. They are very soft. But then once you do these various alloys, and each data point again corresponds to one alloy, the hardness increases quite a bit. And of course, this tells you that the lattice size mismatch or the atomic size difference scales linearly with the hardness increase. This is the important take-home message here. But we want to develop high-temperature alloys. So what about oxidation resistance? Here I've shown you again mass change at 1100 C for these two alloys. The niobium alloy is not so promising, but the tantalum alloy, tantalum, molybdenum, chromium, titanium, aluminum, shows very low mass changes at 1100 Cs. So this should be of interest for further development. First of all, you have to make the alloy, equiaxed coarse-grained grains. You should check again chemical composition, chemical homogeneity. We have done this. I can skip this. We do get, of course, because of the tantalum and the chromium inside there, we do get a hexagonal Lavis phase again. This is chromium to tantalum in this case, and you can see it here as nice little bright spots on the grain boundaries. Of course, you can imagine that this brittle phase on a grain boundary is not good for structural materials, because if you want to plastically deform it, it would fail. And I will show you an example for that in a minute. Now, is this really an A2, meaning a disordered solid solution, A2 crystal structure? No, it's not. As you see here, you have tiny little reflections here and there. Somehow the signs got lost. Here you have some indications of B2 structure. So we do have, here they are. We do have B2 lattice, super lattice reflections, meaning we do not have random distribution of atoms, but some of the atoms take one atomic site and other atoms take another atomic site, preferentially. And now, what is the consequence on the deformation behavior? Here you see stress-strain curves. Everybody should be familiar with that. Stress-strain curves at various temperatures. You see, below 1000 degrees Celsius, you cannot even take a stress-strain curve because the material fails elastically. So it's totally brittle below 1000 degrees C. The reason we guess is we have to avoid this Lavis phase at the grain boundaries. And I will show you briefly in the last 5 minutes how we tried to accomplish it. So we started first with taking out the tantalum completely. No tantalum should be no Lavis phase, right? Because chromium-2 tantalum is the Lavis phase. Again, this alloy is single phase. Again, we have some tiny ordering superlattice reflections, but much less than in the other case. You can hardly see the superlattice reflection spots. There's not much left here in a magnified view. But in SEM, in TEM, you can see it. This is a TEM selected area diffraction micrograph. You see gentle, really not very prominent superlattice spots. So there must be ordering, meaning there's no randomness again in the atomic site occupancy. It's preferred atomic site occupations. So this is the B2 structure, right? A center atom and simple cubic structure. Now, again, the test without tantalum, no Lavis phase, the material should be ductile, right? Well, it's better than it was before, so we could obtain 800 C tests and 600 C, but again, below 600 degrees C, we did not see any ductility in the stress strain curves. So the question you could now pose, is there an influence of B2 order? And we did some calculations with a thermodynamic database to verify whether there is a A2 to B2 transformation at 1150 degrees Celsius. This is what it shows here. There should be the second order phase transformation at 1150 degrees Celsius. So we expect B2 ordered structure to form. Whereas if we reduce the aluminum content, it should be single phase all the way down, all the way up to the melting point and all the way down to the room temperature. So the final 2 slides I'm showing is on this alloy with the reduced aluminum content. This I skip. We can check this by another microstructural characterization method, whether we have an A2 to B2 order transformation by differential scanning calorimetry, for example. When you observe an ordering, you have this lambda-shaped peak here, which is gone here in this case for this alloy. And here you can hardly see it. So alloys containing lesser aluminum than the 25% should not have ordering. So this was the plot shown before. And now, hurrah, we do have some ductility at room temperature. So the material is pretty strong. Here see the scale, 1500 megapascal. So it's as strong as a steel at room temperature, a martensitic steel, but it is still as strong as a high temperature material at high temperatures. Okay, so the take-home message for these alloys is you have to avoid alien phases on the grain boundaries, and you have to avoid B2 ordering, at least when you talk about the matrix behavior. And this is the summary of my second part. I have shown you that there could be a very large atomic size difference ranging up to 5%, which is really huge, which can give rise to high strength levels. Promising oxidation resistance at high temperatures. The atomic size difference correlates well with the hardness difference. B2 forms in these alloys, which is not good. The disordered A2 structure, simple BCC, can be stabilized until room temperature by reducing the aluminum content, and this then gives rise to an increased ductility at these low temperatures. And with that, I'm at the end of my talk. I thank you for your attention, and I thank my group at KIT for their work. I thank our cooperation partners, mainly from University in Siegen in Germany, from the Brown University in Providence, Rhode Island, and from Forschungszentrum Jülich in Germany. I also thank some funding agencies, mostly the German Science Foundation. This is the National Science Foundation in Germany, which gave me some money to these 3 grants. I also thank the Karlsruhe Nano Micro Facility, which also supports Manuel with his work and our work, and the Carl Zeiss Stiftung. Carl Zeiss, you know Zeiss, the optical company, which has also supported this work. Thank you very much.
Now, as usual, we will open the session for questions from the audience. Any questions from the audience?
Here's one.
Yes, there's one question here.
Thank you very much for your nice talk. I'm wondering about you mentioned that one of the roles of aluminum is to create an oxide layer, and also chromium.
Yes, chromium and aluminum.
What are other options do we have for that layer, and how thick this layer should be in order to accomplish its task?
So the beauty of these systems, or the beauty of the beauty of these high temperature alloys, is that they form the oxide layer upon service, meaning you get the pure alloy, so to say, the non-oxidized alloy in the environment, and while you apply it there, it forms an oxide scale. And the question is whether this oxide scale is easily to be penetrated by ingressing oxygen, or whether the oxide scale, once it has formed, protects the alloy from further oxidation. Having said this, there is no oxide which protects 100%. Yeah? Don't believe that, right? There's no oxide scale, either an artificial scale or a naturally grown scale, which protects 100%. But the most protective oxide scales are those formed by aluminum, which is classical alpha alumina, by silicon, which is quite often amorphous silica, and by chromium, which forms chromia, and some mixture of that. So the reason why I was talking about chromium and aluminum is, in this particular case here, the alloy forms chromia scale, but it inherently has a needed minor addition of aluminum in there, which makes the oxide relatively gas tight. So the further oxygen ingression cannot take place easily. This can be studied in fundamental way by these weight gain curves, right? If I would, let me just go back to these weight change curves. Maybe the ones I showed you here would be enough. So here, what you see, this is on a linear scale, mass change over time. But the curve somehow looks like a parabolic shape. So what people in our field do is, we do not plot this linearly. I just wanted to show you the absolute numbers. That's why it's linear here. We plot this on a quadratic scale. So it's delta m square, so the mass change to the square, per unit area to the square, over time linearly. And then you would see that both of these alloys show a linear behavior. And this is an indication for parabolic growth law. And again, this is another indication for that the oxide is protective. You can also have much stronger increases linearly, for example. Linear oxidation would mean if I double the time, I have twice as much mass change. Or in other words, twice as much metal consumption in the same time. What we need is a parabolic scale, so this should become slower and slower and slower, and then after 5,000 hours, there's even not much more metal consumed. Yeah? So you have to check whether you have a parabolic growth law or not. And this alloy does show parabolic growth. And of course, at the moment, in this community, in this scientific community, we know only of these three elements, and some mixtures of it, which show parabolic growth at elevated temperatures. If you find another element, you can become very famous.
Thank you. Just another question regarding the applications. You mentioned that one of those is in turbines, and any other application?
Yeah, so
thank you.
There are several more applications which you can think of. Of course, it all depends on the costs, right? How much does the part cost being made out of this material? To be honest, I'm not looking into the costs business or into the cost calculations, because this is not my business. But in principle, none of these alloying elements are extremely costly. just a side comment on this. For example, if you look at the nickel-based superalloys, they contain rhenium. And rhenium is nearly as expensive as platinum. So here there's no rhenium in there. So you can, of course, avoid the costs of rhenium. Application-wise, we could think of, for example, turbochargers for automotive applications, because they also require very high temperatures on the exhaust side. In fact, most cars now, most modern cars have a turbocharger, but they the gas engines, not the diesel engines, but the gas engines suffer from one problem. The exhaust side, the exhaust temperature of the gas is beyond 1100 C. That means, since these turbocharger wheels are made also out of nickel-based superalloys, they would suffer from not enough strength, so to say. They would go down in performance. So what the people do in the automotive business, and probably they have never told anybody who buys a car with a gas engine, when you run at full speed, they put too much gas into the engine in order to cool down the exhaust gas. Otherwise, you would overheat your turbocharger wheel on the exhaust side. So having other materials which would not need this requirement, would be much more fuel efficient. So that's why when you run a Porsche on German highway, without speed limit, it drinks like hell, when you run it at 250 kilometers per hour. Yeah? Of course, you may argue you cannot do that that often. Believe me, you still can. Yeah. Yeah.
One more question from the audience?
In the back and and here, yeah.
Le pregunté de que si... ok. Bueno, la pregunta que quiero hacer es sobre el costo-beneficio que tiene el hacer esta aleación. Dado sus aplicaciones, pues ya dijo algunas, ¿verdad? Pero quisiera ver si es más el beneficio que el costo que llevaría a hacer este tipo de, avance tecnológico. O sea, más que un avance, pues es una innovación. Entonces, lo que pregunto es qué tanto beneficio tenemos ahorita que no se pueda tener ya.
I think I need a translation, Mark.
Yes. The question is the cost benefit. In other words, like to do an actual application beyond lab work.
Yeah. That can be actually quite precisely answered. If you would increase in this first slide where I showed you the temperature increase with the efficiency increase of the engine, right? I can switch back. I can try to go back. Every 100 degrees Celsius increase would bring you an increase in a reduction in fuel efficiency. Now I got too far. Here, every 100 degrees Celsius gives you an improved fuel efficiency of 5 to 10%. Right? So let's assume you can. So as you see here, the temperatures are much higher than the temperatures a nickel-based superalloy can withstand, right? So there must be alloys which can withstand 1400 degrees Celsius turbine rotor inlet temperature. That's the trick here. It's not the temperature the material sees, it's the turbine inlet temperature which comes out of the combustion chamber, right? So that does not mean that the gas, when it has 1400 degrees Celsius, would transfer all this temperature onto the material, because the material has a heat capacity, the material has a thermal conductivity. So if you subject a metal to a gas which has 1400 degrees Celsius, and you let the heat go into the metal, it would conduct the heat down to the rotor and then move it away. So in fact, during operation, this material is not as hot as 1400 degrees C. It's maybe only 1100. Yeah. So, but if you would go to 1500, and even assuming if you would go along this straight line, we hope that with our uncooled materials we would go parallel to this line, you would benefit by approximately at least 5% of fuel efficiency when increasing the turbine inlet temperature by 100 degrees Celsius. And what I also did not tell is, why is this deviating even more from this ideal performance? The reason is simply that now, for this rotor temperature, you have to apply environmental barrier coating on the metal surface. These are no longer uncooled blades. These blades are really made in a very tricky way. They have cooling holes, you know, they are cooled from the inside to get film cooling on the surface, and they are protected by an environmental and a thermal barrier coating. Environmental barrier coating against oxidation resistance, oxidation attack, and the thermal barrier coating to reduce the temperature of the metal blade, but both come along with a disadvantage in efficiency, or with an increase in inefficiency losses. That's what I did not show on this slide, but this is the reality. So the last uncooled blades were operating here at temperatures below 1100 C. So if we now can use a material which may not need an environmental or thermal barrier coating, we would jump up to about here already. And then if you can go even further, say 100 degrees higher, then you would be here. So that would be a tremendous effect on the efficiency. However, we have not solved all the problems, I should be honest. That's the vision, right? Okay, yeah. There was, yeah?
Thank you, Doctor, for your talk. I was wondering if you have any insight about the atomic positions in the superlattice, or if you have used some atomistic computational methods, or using tomography.
I skipped that because then the presentation would have become definitely too long. What we first did was to try to, well, we did some theoretical calculations about the atomic diffraction diffraction factors of the different atomic species, which you can of course place on a corner of this unit cell or in the middle of the unit cell. Then we have played around with different assumptions, say molybdenum and aluminum would go on one side, chromium and titanium would go on the other side, and then we mixed it around, so molybdenum, chromium on one side and aluminum and titanium on the other side. And what we found out surprisingly is that due to the diffraction factors of these atomic species, we cannot see the superlattice reflections in the X-ray diffraction diagrams. And even in the transmission electron diagram, micrographs, we see only very gentle superlattice spots, right? So it's very hard to quantitatively predict which atoms assume which lattice sites, right? So we then tried, and this has been published in the paper which we have recently done in Acta Materialia, again another paper from this year. Let me see, I need to go a little bit forward again. No, not this one. This one here. In 2019, this has been published in this paper in Acta Materialia. With high-resolution transmission electron microscopy, you can get an idea about which atom sits on which lattice site, but it's still hard. And it's also hard with atom probe tomography. It's because we do not have, probably we would need help from DFT guys in this matter. Yeah.
Why not EXAFS analysis?
We did not have the chance to use EXAFS, but that would be another option, right? So.
Any more questions from the audience? Yes.
Well, thank you for your talk. And my question is about the passivation layer of the alloy? Because as I understand, the aluminum is used to form an alumina oxide on the layer of the alloy. But my question is about the chemical composition of this oxide layer, because, well, by the reason it is an alloy, I wonder if another oxides form on the passivation layer, and well, I don't know if that oxides could affect the oxidation rate of the alloy, and well, I think of, for example, doing an X-ray for electron spectroscopy to analyze the composition of the oxide layer. I don't know what more information can be.
Yes. You are fully right, and I tried to keep the story short because I was talking already probably too long. But in this case, for example, what we know in this quinary alloy with the tantalum, we know that we form, again to our surprise, a very stable, that's why I said before, usually you form either alumina or chromia or silica with some other ingredients, but the major cationic component would be aluminum, chromium or silicon respectively. Here it's different. The tantalum plays a decisive role here. Here we get a chromium tantalate, CrTA04, a mixed oxide consisting of chromium 203 and tantalum O2, tantalum oxide, which seems to be the most stable oxide in this particular situation. So you are fully right. It's not that easy that you say, I put 20% aluminum in there and then I get an alumina scale. Of course, it's the activity of the elements in the respective alloy. But what I said before is, some aluminum still may help because it affects the rate of how fast the oxide scale is formed on the surface layer. And then, of course, you have to go into all the details and really exactly detect what kind of oxide you have on the surface. And in the other case, the molybdenum silicon titanium alloy, we still do not understand fully why this alloy is so oxidation resistant, because I mentioned this earlier, we tried to set up a model for discriminating the oxide scale thickness which forms on the outside and which forms on the inside. I skipped this due to the sake of time, but there's some internal oxidation also. But what we still have not understood is why in this composition, you see here you have a majority of titania, and the blue color is titanium oxide. The orange color is silicon oxide. So actually the majority phase is the blue titanium oxide scale, and still you get a decent oxidation protection. And this is totally unexpected when you use pure titanium, for example, put it in the furnace and form a pure titanium, a rutile titania oxide on, rutile is the name, of the crystal structure. When you form this, you would expect much higher growth rates. So my suspicion is this blue titania has a majority of titanium cations, but it's not pure titania. There should be some silicon atoms or others incorporated in the scale, and this is why it makes it so oxidation resistant. We have not, it's quite difficult, this is the oxide scale. Here below is the metal alloy. This is all oxide scale. So, and we have used color coding, of course, false color coding to discriminate between titanium and silica. You can do this by EBSD, for example, electron backscatter diffraction. You see the titania peaks, and everything which is amorphous is assumed to be silica. But still, what was the point I was going to answer? If it were pure titania, then it should oxidize much more rapid. So there must be something else going on, but we did not have the... okay. And since this is a complicated microstructure on a fine scale, it's very hard to, focus on only one phase without getting disturbing impact or influence from the other phase. When you do, for example, an energy dispersive analysis, you cannot do it with that. We will now go into atom probe tomography again, and then by luck, for example, we just measure titania, or if we measure a region where you have titania first and then silica next, then you can see the whole change of the chemical composition. But again, ask him how easy it is to prepare an oxide for atom probe tomography. Atom probe tomography, you make a very thin needle, you know, the needle is nanometer thin, and then you pull out one atom after the other in a high electric field. The atoms then transform into ions, right? You pull them out and then you use mass spectrometry to analyze the chemical result. This complex interwoven structures, I would be happy to take this advice. But my view of this is too simple, the picture. It's neither pure silica nor pure titania. But in a combination between silica and titania, it performs extremely well. And this was not shown in literature before. Because in literature, people studied, for example, molybdenum 3 silicon, and then, of course, they studied the growth of a silica scale. Or they studied titanium 5 silicon 3 and made only titanium oxide, pure titanium oxide. Again, this doesn't show oxidation protection. And then the other thing is, it also depends on the mismatch of the thermal expansion between substrate, metal, and oxide, right? If the substrate expands very strongly, then it cracks the whole oxide on the surface. When it cracks the oxide, then you have free paths where oxygen can attack the metal substrate. Obviously, and this is another idea which we follow along, is that the metal underneath and the oxide have similar coefficients of thermal expansions, similar low coefficients of thermal expansions. Oxide are known to have low coefficients of thermal expansions. Metals are known to have high coefficients of thermal expansions. Molybdenum, tungsten-based alloys have very low coefficients of thermal expansion coefficients. That's why we can use that in these lamps, which are giving these nice views here, right? These are tungsten electrode arc lamps, right, which have to operate under protective atmosphere, under argon or some special gas. You now know why, because if there would be air inside, this tungsten would oxidize rapidly to tungsten trioxide. It would evaporate, and then your cathode, your tungsten cathode, would operate only 10 minutes. And have you ever seen such a lamp explode? Yeah. No? Well, we don't try now, but if you would see it, there would be white smoke coming out, right? And it would make boom, and then it's gone. You know, operation stops immediately. There's no protection due to oxide formation in these simple refractory metals, but they have the highest melting points, so they are attractive from this point of view. Okay? Maybe this answers your question, at least to some extent.
What about
okay.
grazing incidents?
Yeah, grazing incidents, we do not have a facility for that, but we can try this as well, yeah. We have talked to our cooperation partners in Darmstadt who have this. With grazing incidents, X-ray diffraction, you might found, but then you only know the lattice parameters. Then you don't know how much silicon, or is it silicon at all, which is in titanium.
I was thinking electrons, not
Okay, we haven't tried it out, yeah. Good point.
Okay, for now we finish the talk, and we thank again Professor Heilmaier for this wonderful talk.
Thank you.
There's a lot of questions, of course, and you're welcome to either send an email or approach him afterwards. And in particular, I wanted to thank all the students, the grad students, undergrad students, the faculty members for being here and make this lectureship possible, as well for the support from the director, Professor Juan, and as well from, as you heard from the rector, all the support we have to celebrate this lectureship. Thank you again, Mark.
Can I? Yeah. I want to make a final announcement. No worries, it's pretty short. If some of you, by accident, is interested in making a stay in a foreign country, in particular in Germany, of course, and is really willing to go somewhere either on a student level, I mean master student level or PhD candidate level, and you find a suitable topic, just send me an email. Manuel has my email address, and I will try to make something happen. It must not necessarily be here in my institute, because we are doing some structural materials. If you are more in functional materials or whatever, don't hesitate to contact me. We have always some possibilities open for exchange students over the summer whatsoever. This was mentioned before, but I just wanted to express this once more again. So I can really encourage you to try and take the chance, if you have it, to go to a foreign country for at least a couple of months, because it broadens the horizon quite a bit. Thank you.
Briefly adding to this comment, I was there last year during my sabbatical. Find out that Germany.
Take the microphone.
All over the country, you can move anytime during the day, and it's relatively not that expensive. And they have a great train system. You can go anywhere by train. You can go easy 3 hours to Paris, Strasbourg 45 minutes, Stuttgart 30 minutes. They have many great cities. Most of the cities are colonial cities, so they have this castle and downtown and all these touristic areas. And also one particular thing that I found out in Germany, all the rivers crosses the city. And this is very romantic, beautiful, because you got water in the city, natural water coming from the ocean, from the lakes. And then also, they have a lot of sites for mountaineer trails. You go on the mountains walking, and they have these hostels on the mountains and all these things. So overall, it's a great experience. I encourage you to go for summer. They have a lot of Mexicans there, especially from Puebla and Monterrey. The Tec de Monterrey has already a partnership with KIT. I met a lot of undergrads at the Mensa. They call it Mensa, the cafeteria. Mm-hmm. And obviously we were talking Spanish and saying "güey" all the time. I was like, "Where are you guys from?" "Oh, we're from Monterrey." "Oh, I'm from Juárez." And so you can find also connationals there, and you don't feel this alone, like thrown in one city where you're not going to be able to communicate or anything. Everything is done by bike. Also, yes. They promote the bikes a lot. I end up knowing that having a bike is like having a vehicle. When I had my bike, I started making more friends, because then I feel like I have a vehicle. So you can commute in the city easy. And as I said, it's very safe. And the KIT people are very hospitable people. And the tools they have, and as you see, the quality of research really expands your knowledge beyond what we offer here, which is a lot too. And I encourage you also to start doing research with some of the faculty members here. We have strong faculty members, and we are adding more equipment, more tools to do high advanced research as well. Thank you so much.
Thank you.